Hello there, this is Ms. Nakayama, and today's lesson is 11.4, three-dimensional figures. So this begins our study. As I mentioned, the first part of our chapter was two-dimensional figures. Now we're on to three dimensions. So, as I just said, a 3D figure or three-dimensional figure or solid is bounded by flat or curved surfaces that enclose a single region or space. We are going to concentrate our discussions on polyhedron, which is a three-dimensional figure or solid whose surfaces are all polygons. So when you look down here real quick, okay, these are types of solids, but you have those that are all polygons and those that have shapes that are not polygons, i.e. a circle or three-dimensional sphere. So if it has whose surfaces are only if the surfaces are only polygons, then we call them polyhedra, plural of polyhedron. Otherwise, they are not polyhedra. So we're going to be studying just polyhedron. So first off, we're going to make sure we know our vocab. So a vertex, plural vertices, of our three-dimensional figure are any of the letters in that figure. So if you are asked to give them D, E, F, G, H. Order does not matter when you're listing the vertices. An edge is any segment in our figure. So DE, we got segment DE, segment EF, segment FG, segment GD, segment HD, segment HE, segment HF, and segment HG. So if you know these things, y'all, you can pause or write them down, check them, might make the video go a little bit faster. Our faces, okay? So if you look at this particular solid polyhedron, we have four triangles that are all connected to a bottom, which is just a quadrilateral because you don't know anything about it. So that gives us triangle DEH, triangle HEF, triangle HFG, triangle DGH, and then quadrilateral DEFG. Okay, so to name a prism or pyramid, you use the shape of the base. The two bases of a prism are congruent polygons in parallel planes, and that's really important, y'all, because that's going to help you know what it's called. The base of a pyramid is always a polygon. So the difference in our prism, these two bases that they're pointing to are pentagons. They are congruent polygons in parallel planes. A pyramid, on the other hand, has just one base, but all of its faces are triangles, and it comes up to a point. So we have congruent bases are our top and bottom, if you wish to think about it. And then the lateral surface area, which is on the sides, are always rectangles. In here, we have the bottom is whatever shape it is, but the lateral area this time is always triangles. So if we always name it by the bases that are pentagons is going to be called a pentagonal prism. Okay? Prism, the lateral faces are rectangles. On the other hand, if it comes to a point, then it is called a pyramid. In this case, the base is a triangle, so it is called a triangular pyramid. So, look at our examples, tell whether each solid is a polyhedron. If it is, name the polyhedron. So remember, polyhedron means everything's made of polygons, and I don't have any curves. So the first one, yes, it is a polyhedron, and it is called the base of which all four sides are the same, and I have right angles, so it would be called a square pyramid. Next, I've got a curve, so it is not a polyhedron. Next, I have, it's a prism. Prism, or is it a prism, or is it a pyramid? Okay, the pyramid comes to a point. This one doesn't. I have a triangle here, and I have a triangle here. They are congruent triangles, and that means that this is, yes, it is a polyhedron, and it is a triangular prism. All right, next, all of the faces are polygons. So yes, it is a polyhedron. The base is a 1, 2, 3, 4, 5 side, so that makes it a pentagonal pyramid. No, I've got curves in there. Okay, Yes, this is a polyhedron. All right, this right here is a hexagon, and that right there is a hexagon, and all the other ones are rectangles. So my two hexagons are my base, and that's how I name it. So it's a hexagonal prism. All right, next, cross sections. You've got to be able to look at a picture, y'all, and know this is just building into your math learning in your future. Cross sections, the intersections of a solid and a plane. The result is a two-dimensional figure. So if I have this, for lack of a better word, donut, a real live donut, and I slice it with a knife or a plane, if you think about what's going to show up on that knife, and it's going to look like a two-dimensional donut. All right, on B. And again, pause, y'all, and see if you can go draw these intersections and then play it and check your work. This one, what's going to show up on that plane is a triangle. This one is going to give you a rectangle. The next one is going to give you what y'all would call an oval, but in math we actually call it an ellipse. You'll learn more about that later. And this one is a circle. So the difference that we have between these two is this plane is not parallel to my base. This plane is parallel to my base, which is why I have a circle. All right, turn your papers over. Describe the shape formed by the intersection of the plane and the solid. All right, the key here, y'all, is it said describe. It didn't say to draw it, so you're going to use your words. And so the shape that's going to be formed by the intersection of the plane and the solid in this case is what I see on that base, and that is a pentagon. Next, it is parallel to the bottom, and that bottom has 6 sides, so it is a hexagon. This one is a sphere cut by a plane, and that is going to give us a circle. This one, if you think about what you can see, it's kind of shaded purple here, so that would be a semicircle. And then last but not least, this shaded region is a pentagon. All right, so the other thing you got to be able to do is kind of go the other way. We were taking 3-dimensional and going into 2-dimensional. Now we're going to talk about 2-dimensional and go into 3-dimensional. So a solid of revolution is a 3-dimensional figure that is formed by rotating a 2-dimensional shape. So this guy right here is a 2-dimensional shape. I think I can see it with this. Is a 2-dimensional shape. And if you rotate it around, which is what that's partially doing, okay, the direction doesn't matter, okay, the line around which the shape is rotated is called your axis of rotation. But what you've got to do is be able to draw and see those figures. So, sketch the solid produced by rotating the figure around the given axis. So again, pause, see if you can do one. Do one at a time, check your work. Okay, you'll get more out of this. So if I take that and I rotate it around the given axis, which is along the 4 here, then my figure is going to look like this. Somewhere, LOL. All right, so it's that. You can see that this is my axis of revolution and this one is going like that. So this, of course, is a cone. It has a radius of 3 and a height of 4. The next one, 13, is kind of like what you saw up here, so hopefully that was easy for you. If I were to draw it, I'm going to draw a cylinder where it has a height of 8. I don't know why that didn't go all the way to the middle, but this, so a cylinder with a height of 8 and a radius of 6. All right, this guy, rotating it around, kind of hard to show you that on a, I can't do that very well on a video, but you'll see, hopefully. But when you rotate it all around, if you twirl that around, they make these funny little figures you can do this with in decorating. But it's going to make a sphere, and that sphere is going to have a radius of 7. All right, number 15, another cone, because I'm rotating it this time around that vertical axis of 6. So my cone has a radius of 4 and a height of 6. And then last but not least, number 16 is very similar to number 14. So it is another sphere, just rotating it on a vertical axis instead of horizontal, sphere with a radius of 5. So one of the things that we need to talk about with 3-dimensional figures is something called Euler's theorem. Y'all, it's not Euler, it's Euler. He's a Swiss mathematician. Okay, and the formula says F plus V equals E plus 2. What does F mean? It's the number of faces V is the number of vertices, and E is the number of edges. So it's a pretty straightforward formula. I'll go ahead and highlight that formula again. F plus V equals E plus 2. So I know V, I know E, and I'm looking for F. So I'm just going to plug into the formula. I'm looking for F plus V, which is 6, equals E, which is 12, plus 2. So when you solve that, that gives you 18, 6. 18 minus 6 is 12. Oh, that's 14. Good thing I can add. I was looking at the 6. 14 minus 6 is 8. Thank you all for being understanding. All right, number 18. A polyhedron, these are the last two, y'all. A polyhedron has 20 faces that are all triangles. How many vertices does it have? So we're using our same Euler's formula, F plus V equals E plus 2. So I start off with F, and I have 20 faces. F plus V, how many vertices? That's what I'm looking for. E, how many edges? They don't tell us how many edges, but what they do tell us is how many faces. And I know that if I have 20 faces and they are triangles, then that's going to be 20 times 3 edges. But some of those edges are going to connect to each other. So if you think about this up here, I mean any of these, okay? This right here, this is a triangle, and this is a triangle, but they share an edge, and this shares an edge with that. So if you think about it, you're going to end up actually needing to divide the number of edges by 2 to find out how many you have. So when you do that, you get 30. So I'm going to plug that in my formula. 30 plus 2. 30 plus 2 is 32, and 32 minus 20 is 12. And so that means that we have 12 vertices. All right, last one. A polyhedron has 14 faces, 8 are triangles, and 6 are octagons. How many vertices does it have? So again, I'm going to plug into my formula, and I have 14 F faces. 14 faces, it told me that, plus F plus V, got to go find, that's what I'm looking for, my vertices, equals the edges. So let's come back over here to my edges, and I have 8 triangles, so that's going to be 8 times 3, plus 6 octagons is going to be 6 times 8, and remember they share a side together, so I got to divide that by 2. That's going to give me 36, so I plug 36 into my formula, plus 2. 36 plus 2 is 38, and 38 minus 14 is 24, so we have 24 vertices. And that is all that we have for 11.4, three-dimensional figures. Thank you so much for watching. Please don't hesitate to email me or come see me if you have any questions. Y'all have a great day.